Yeah, okay. So welcome everyone to this colloquium series, which is organized by the Asia Pacific Center for Theoretical Physics in Pohang, South Korea. And I was kindly asked to the host and chair the the talk today, which will be given by Professor Mark Srednicki. And let me come first to a few facts from the biography of Mark, so that for those of you who are not so much familiar with him, Mark did his the PhD at Stanford University, coming before from Cornell University, and then he moved on to work at Princeton University as a postdoc. Then he worked for some 2 years or so at CERN. And then he moved to the University of California at Santa Barbara, where he essentially stayed since and is now a full professor of physics at the UCSB. Mark is very well known in the physics community. He is an expert in quantum field theory. He is one of the first inventors of the axion, which is maybe will be measured at some point later to explain problems in dark matter. But he also at some point became very much interested in thermalization, as we just discussed before the talk started, because of teaching. And there were some open issues arising from these questions of how things thermalize. And these brought him first to quantum chaos and then to quantum thermalization, which also comes under the nickname of ETH, which is not Eidgenössische Technische Hochschule, but is eigenstate thermalization hypothesis, for which he is very, very much well known in a broad physics community. I should also maybe mention that I don't have the entire list of all the papers he produced, and but the few I just see by looking at Google Scholar are amazing. So he has papers on the strong CP problem with harmless axion, which are cited more than 3,000 times. And the famous paper on chaos and quantum thermalization is a run-up and very close to it, almost 3,000 citations. So with that, maybe I should just also mention that the talk today will be around the eigenstate thermalization hypothesis. The hypothesis is not appearing in the title of the talk, so we can actually assume that it's much more nowadays than a hypothesis. And with this, I should maybe give the floor to Mark. And we are looking very much forward to learn more about quantum chaos and eigenstate thermalization. Mark, the floor is yours, please.
Thank you very much for that very kind and generous introduction. It's true, I don't have the word hypothesis in my title. I did coin the phrase eigenstate thermalization. Other people added hypothesis. I thought it was just a fact, but I will tell you the story. So the story, as mentioned, is that my work and my career was all in particle physics and dark matter and things like that. And then one year I got assigned to teach statistical mechanics, which I'd never taught before, but I thought this would be fun. And so I started preparing to teach it. And as I was preparing to teach it, I slowly realized there were many things I didn't understand about it. And my understanding was not cleared up, or my lack of understanding was not sufficiently cleared up by reading various books that I could find in the library. And that annoyed me. And so I started to try to figure it out for myself. And so what I'm going to tell you today is that story of how I thought about it. This is now an old story, and I understand that many in the audience are experts. So I want to warn the experts, I am not going to say anything that you don't already know. This is a colloquium intended for people who are not experts. But I hope it will at least be of some perhaps historical value to those of you who are. So the question I want to pose is, how do isolated many-body quantum systems come to thermal equilibrium? So a very simple example, and of course, thinking about this sort of problem goes all the way back to Boltzmann and many other people of that era. Let's suppose we have some atoms, and I want to think of them as something with short range repulsive interactions. We could think of them as hard spheres. And I'm going to put them in the box in the lower left corner moving up. And then we know if we wait a little bit, and we know this because we do the experiment, the atoms will bounce around, and eventually, not too much time is necessary even, they will be more or less uniformly distributed in the box and with a thermal distribution of momentum. So how do we understand this process? And I had, back when I'd gotten this teaching assignment, I had some vague notion about how this was supposed to work classically. The atoms hit each other, and then there were words one could say like ergodicity and chaos, and somehow this would all work out. But I didn't know even what words I was supposed to say in the quantum mechanical case. Coming out of high energy theory and particle physics, I think of everything in terms of quantum mechanics. So I wanted to know, how would you solve this problem quantum mechanically, and how would you understand this as a quantum mechanical process if all you knew was quantum mechanics and nobody had ever taught you statistical mechanics? How would you understand this? And I slowly realized again that I didn't know, and I couldn't find an answer that I found convincing in the textbooks, so I set out to figure it out. Okay, and now, there we go. All right, so we're going to start with some basic assumptions. First of all, I'm going to say this in a somewhat more abstract language than a particular model. But we're going to have many degrees of freedom, and we don't need to be super precise about this. So if we have n atoms in the box, we could say n is the number of atoms, or if we have n coupled spins, we could say n is the number of spins. I'm not going to worry about order 1 factors in this definition. And then we have some set of observables, and I call observables A for no particular reason. And I here is supposed to be an index that tells us which observable we're talking about. And for example, in the gas problem, one of them could be a number operator that counts the number of particles with a given momentum. Here I'm thinking of the momenta as discrete, so there's some discrete label on the momenta, and we're just going to count the number of particles that have that momentum. That's the sort of thing I have in mind. For spin systems, it would be components of different spins. But I want to think of these things as physical things that one could imagine measuring. Or if one is a theorist like me, can imagine, as a caricature of what an experimentalist could measure. But what I don't want to allow is just some completely abstract operator that does not have some physical definition. Okay. Then there's going to be some quantum state, and I will take the quantum state to be a pure state. That's not strictly necessary, but the sort of paradoxes that one encounters when thinking about this are sharpest for the case of a pure state. So it will be useful to think about a pure state. And we'll work in the Schrodinger picture so that the state is time dependent. And then the set of quantities we'll look at are the instantaneous quantum expectation values of each of our observables. Now, an experimentalist might complain that, well, we don't really measure expectation values, and this is true, but I want to use these as at least as indicators of what one could measure. And so again, these will be the mathematical objects we'll look at, and we are going to make an assumption that these are indicative of the physics and not spend time worrying about measurement theory or how a real experiment would actually be carried out. We could, of course, go back and do that, but at least for now, I'm not going to. All right. Now we can define total energy for the system, which is just the expectation value of the Hamiltonian. I'm going to assume the Hamiltonian is time independent. We just have a fixed system and we're just letting it evolve in time under the Schrodinger equation. And with a Hamiltonian that itself does not have any time dependence. So this expectation value is in fact time independent in that case. And I'm going to assume that it's scaling like the number of degrees of freedom. So I have a finite amount of energy per degree of freedom. Or in thermodynamic language, there's a finite temperature, a non-zero temperature. That's a temperature of order 1. It's not exceptionally small. That corresponds to having a finite amount of energy per degree of freedom. Now, it's quantum mechanics, so there are quantum uncertainties, and the total energy has a quantum uncertainty, which we could compute using the usual textbook formula, which is this. And I'm going to assume that this is small in the sense that it scales like the number of degrees of freedom to some power that's strictly less than 1. A natural thing for this to do is to scale like n to the 1/2. If the Hamiltonian is a sum of local terms in some sense, and different terms that are far away in whatever sense that means are uncorrelated, then this will naturally come out to be the square root of n. And similarly, if one takes a thermal expectation value using the canonical ensemble, or really any, well, I guess we want to use the canonical ensemble, you will again find that a square root of n for this. So that's the natural thing. But for us, the important thing is going to be that I can think of it as small. So when I think of there being many particles, so many that whatever this exponent is, when it's less than 1, I can go to an n large enough that this is small.
Simple
Okay.
question.
Yes.
Question? So if the Hamiltonian is not written in terms of local terms, then gamma is different from 1/2. Can you give me more examples, or also
we can certainly find states in the Hilbert space for which it will be 1. Maybe if I should press my next button here. Yes. So these two statements are both restrictions on the set of states I'm going to consider. I want to consider only states that have a large enough energy that there's a finite amount per degree of freedom, and I want to consider only states that have a small in this sense quantum energy uncertainty. So these are restrictions on the class of states I'm going to allow myself to consider. I want to claim that these are quite mild restrictions, and that most anything you could actually construct would satisfy these things.
Yeah, I understand the problem setting itself, but my question is just about curiosity. So is there any example? So in the central limit theorem, we know that gamma is 1/2 in the Gaussian distribution, or some So if I consider some long range, some hopping model, then gamma is different from 1/2. Because
this is really just a statement of, if I just take my initial state, and I'll show this on another slide in a minute. If I just take my initial state and expand it in energy eigenstates, I'm restricting myself to a class of energy eigenstates, to superpositions of energy eigenstates where the range of energies that I'm superposing is small compared to the total energy. And that's just a restriction I am putting on my class of initial states. But if you had if you said, no, I don't want to do that, I want a state where the energy uncertainty is large, if even thermodynamically, you would now not be able to define a well-defined temperature, right? Because if the energy of the system is not well-defined, the temperature is not well-defined. So even though states like that exist, we don't expect them to correspond to conventional statistical mechanics, which is what I'm trying to derive.
I see. Okay. Thank you.
If I may add,
Yeah.
I think what Kisiok was actually pointing to is whether there are systems, Hamiltonians, where you never find those states which satisfy these conditions which you describe here, which means that you have long-range connectivity in your Hamiltonian, so that there are practically no states which, and then you have, of course, again, problems also with statistical mechanics and canonical and so on.
I think that's a different exponent, right? This
Right.
just says we have a range of energies, right?
Right.
From 0 to some high energy, and the energy levels are populated everywhere in between. And now I'm just going to look at a thin band of energies.
Right.
And, so unless your system is such that, you have only very low energies and very high energies, and you must superpose two of them, only in some extreme case like that will this fail, will these states fail to exist.
Okay.
Yeah, okay, thank you.
Okay, so the goal is to understand results of StatMech. So we're going to need some stuff from, some stuff from StatMech. I'm going to define a thermal expectation value in the usual way, but using this somewhat unusual notation as just the usual canonical thermal expectation value as shown here, traces with e to the minus beta h. And where beta, the inverse temperature, is fixed by the condition that the thermal expectation value of the Hamiltonian has the energy value that the system actually has according to its quantum state. So we have an actual quantum state that has some energy with some suitably small uncertainty in that energy. And then we fix the temperature by this condition. And this is just the usual thermodynamic relation between energy and temperature. And again, as I said, these are restrictions on the state. Okay, now I need a definition of thermal equilibrium, and this is the one I'm going to use. I discovered early on in this that if I was having a conversation with someone, it was often the case that that person and I were using different definitions of thermal equilibrium, and so we would talk past each other a lot. So my definition of thermal equilibrium, first of all, it's time dependent. It applies at a specific time. So if a system that you think is in thermal equilibrium then has a large fluctuation, all the air in the room moves into the corner spontaneously, then it will not be in thermal equilibrium anymore, according to this definition. Of course, then later the air will probably come back and then it will be in thermal equilibrium. So the definition is that the actual instantaneous quantum expectation values of each of our observables that we've chosen on our list is equal to its thermal value at the temperature that corresponds to the system's total energy within some tolerance, because we can't expect exact equality, and an experimentalist couldn't verify exact equality. So we have to have some sort of experimental tolerance. And again, we'll do this for each.
Sorry, Mark, but why not? At certain times there should be exact equality holding, right?
Well, there could be exact equality. It's just that I'm trying to develop.
This left-hand side is a function of time.
Yes.
So it should at some point be exactly equal to this thermal average.
Well, it will be exactly equal, but it's going to fluctuate a little bit.
Yes. It will always fluctuate.
So I'm saying if the fluctuations are small enough, we're going to tolerate them. And we're not going to say if it's, if it's a tiny bit off, that's out of equilibrium.
I see. Thanks.
Oh, there is a hand raised.
Yes, I have a simple question related to the previous slide. would things depend on which observable A do you choose? Because I would naturally expect that the tolerance you mentioned might be different for different operators. So is there like, look, would you request locality of the operator A? Or
sure, we can request locality. My thing is that it should be something you could imagine an experimentalist could actually measure somehow. So not some matrix you make up in some basis mathematically, right? It should have some physical significance. So in a spin system, local spins, right? In quantum computing language, K local observables, something you build out of no more than K, where K is a number of order 1 basic quantities.
okay.
Yeah, and yes, the tolerance is going to depend on what it is, right? And and again, I have in mind some caricature of an experiment that one could actually do. If you ask an experimentalist to measure something, they're not going to give you an exact value. So we have to build in that sort of tolerance.
Okay, thanks.
Yep. Okay, so what do we expect? Well, again, as an example, we could count the number of particles with a particular momentum, and if that momentum corresponded to the particles in the gas moving up, then we would have a lot of those at time 0. This picture is an artist's conception. And what do we expect to happen? Well, we expect, because we took the class in StatMech, or because we live in the real world and have observed similar things a lot, we expect this quantum expectation value will move to its thermal value, and then it's going to sit there most of the time, but with fluctuations. We can't expect it to be exactly equal, but the fluctuation should be small in some suitable sense, so that they can be within our tolerance that we were just talking about. And we expect this to continue for a long, long time, and maybe occasionally there will be very large fluctuations, but those should be rare. Okay, so this is what we expect. And the question I want to ask is, can we get this picture out of quantum mechanics without placing any further restrictions on the quantum state? Or what needs to be true about our quantum system so that the quantum mechanical calculation we could do in principle, although rarely in practice, but if we could do it, that the result of the calculation would be this picture. Okay, so basic ingredients, we have a Hamiltonian, it's got energy eigenstates. I'm going to assume the energies are all discrete because I want my system to be finite size, and finite size systems typically have discrete eigenvalues. I'm also going to assume they're non-degenerate, that any symmetries the system might have that would lead to degeneracies are broken. If we have a rectangular box, we put some dents in it so it doesn't have exact rectangular symmetry anymore. This is more for convenience. It's not strictly necessary, but I'm going to assume it anyway. Yes.
Sorry. So I just wanted to understand this largeness of fluctuation that you are talking about. So mathematically, do you demand that the fluctuation over the mean value should go to 0?
No, I will tell you later what the fluctuations do.
I see. Okay.
Well, they'll go to 0 in a large n limit, but this is worth mentioning probably. I want to work always with finite n, because people like to talk about the thermodynamic limit, but different things scale differently with n. And so you have to decide how things are scaling. And if you have to before you can take the limit, right? And since you have to figure out how they're scaling anyway, we may as well just keep n finite, which is what it means to scale things, right? So I don't want to use the thermodynamic limit as a crutch. I want to be able to understand what's going on at large but finite n.
I see. Thanks.
Okay, So time evolution, because the Hamiltonian is time independent, the time evolution is formally trivial. We just throw in these time dependent phases. And here I am showing my roots in high energy theory by setting h bar equal to 1. I left out the h bar, 1 over h bar in the phase. And now we can just write down this quantum expectation value in this formal sense. Here it is. I've broken it up into two terms. One diagonal term where the two indices are equal, and an off-diagonal term where they're different. And this A alpha beta notation, this is just the matrix element of A between two different energy eigenstates. And again, here's the picture. And the question is, how can we get the formula to agree with the picture? And so back when I was first thinking about this, I spent a lot of time staring at the formula and staring at the picture. And if you stare at it long enough, I claim you will come first to the following conclusion. This first term in the formula is time independent. If I look at the picture, what's time independent about it is this thermal value that the system comes to. So we could imagine taking a very long time average. And if we take a very long time average of the formula, these time dependent phases will all wash out or integrate to 0. Again, I've assumed the energies are all non-degenerate. Now, in practice, these energy spacings are extremely small. They're exponentially small in the number of particles, or degrees of freedom more generally. So that time average is a really, really long time average. It's not a time average that corresponds to any sort of experimental time average. This is purely a theorist's tool to take that very long time average. But happily, I'm a theorist and many of you are theorists, so we can do that. And we take a similar very long time average of the picture, we're going to get this thermal value. So the conclusion must be that this first diagonal term is equal to the thermal expectation value. Okay, and then what's left, the time-dependent part, has to describe what I'll call fluctuations. Both the small quote, small unquote, I haven't defined what small means yet, small fluctuations that are common and the rare fluctuations that are large. All of those are somewhere in here. But now even at this first equality, we have a problem or a puzzle. The puzzle is this thermal expectation value knows almost nothing about the quantum state. The only thing I needed to know about the quantum state to compute it was the total energy, because I needed to know what the inverse temperature, I should use, or temperature I should use when taking the thermal expectation value. And that's fixed by the total energy. But that's all I need to know to compute this number. On the other hand, to compute this number from the quantum formula, it looks like I need to know a lot. I need to know what all these C alphas are. And the C alphas are different for different initial states. So how can it be that this first term is equal to the second term? Or first expression is equal to the second expression. And now I'm going to just make a working assumption that I'm going to just completely pull out of a hat that I'm not justifying at all yet, which is, let's suppose that these diagonal matrix elements, these are just the expectation values of A in a given energy eigenstate. Suppose, and again, this is an artist's conception picture here. Let's suppose if we plotted them versus the energy, the corresponding energy eigenvalue, they would lie on a smooth curve. Let's just suppose that's true. And now I can plot the C alpha squareds on the same plot. And the C alpha squareds, they can jump around crazily or however they want, because we got to pick the initial state. But they should, according to the notion that there's a specific limit on the energy uncertainty, they should have some width that's, this distribution should have some width that tells us what the energy uncertainty is. And now the point is, because these A alpha alphas are varying slowly over this scale, and really this is what smallness of delta E means. It means that the corresponding A alpha alpha should vary slowly on that scale. Now it doesn't matter what the precise C alpha squareds are, because when I go to multiply them by the A alpha alphas are all the same, essentially. So the jumping around of these C alpha squareds doesn't matter. So the conclusion is that if these diagonal matrix elements vary smoothly with alpha or equivalently with E alpha, and the quantum energy uncertainty is suitably small, then this sum of the C alpha squareds times the A alpha alphas only depends on the total energy. And then another piece of the conclusion is that it must actually then equal the thermal expectation value. And this is not so obvious, but the reason it's true is that a set of C alpha squareds I could choose is Boltzmann weights, e to the minus beta E alpha. Now, if I plot those on the picture, those of course are going to lie on an exponential curve, and it doesn't look like they're giving a small delta E. But this artist conception is inaccurate in an important sense. Here, these are all equally spaced, but in fact, the energy density is growing exponentially. So they should be much closer spaced to the right than they are to the left. And then the exponential fall of the weights combined with the exponential growth of the density of states combines to give you a delta E that actually does have this root n property and therefore is small compared to E itself, which scales like n. And so Boltzmann weights are a set of C alpha squareds that I could use to do this computation. And since the answer doesn't depend on the details of what they are, this quantity must in fact equal the thermal expectation value, up to errors that are controlled by the size of delta E. So this is all up to things that depend on delta E being small. Okay, and this is a key punchline. This is what is called eigenstate thermalization.
There's a question, Mark. There's a question by Kisyok.
Oh, yeah. So usually when we discuss this concept, so suppose we consider some big quantum system and separate the two subsystems, and we see only one part. Then we evolve. Then following your argument, so is this partitioning concept is introduced in your calculation? And fixing photon energy. That's the so how that kind of pure is introduced in your
You can talk about subsystems by restricting your set of observables to live in a particular subsystem, right? So if I say I can only make measurements on a subsystem, I will just choose all my observables from that subsystem, and so then all the.
So in your general discussion, if I consider the full quantum system, so I still don't understand how the pure quantum system can evolve in that way. I mean,
well, so far I've made the following claim, right? So if we go back, and let's see, where are we? No, sorry, there we go. Okay, so far all I've said is this is a formula. This is an exact formula. It's always true. I would like to know under what circumstances this formula yields this picture. And the first thing to understand is how this first term equals a thermal expectation value. And my claim that I'm now making is we can understand that if it happens that these diagonal matrix elements vary smoothly with energy. And then we can tell this story, and we do have a suitably small quantum energy uncertainty. Then the idea is it doesn't matter what the C alpha squareds are because they're all multiplying essentially the same number. The red number is always the same, and sorry, the blue number is always the same. And so it doesn't matter that the red number varies. And then we can reach this conclusion.
So in your opinion, we don't have to separate a full quantum system into partitions. So regardless whatever the procedure is, anyway, the eigenstate will be thermalized.
Well, what we need to do is decide on what a set of observables is.
I see.
And all of these notions are, and at one point I forgot to say this, I dropped the index on I dropped the index I on A. So I'm now just looking at one of them, but we should do this for the set. But you have to tell me before we start, what is your set of observables that you are going to use to decide whether your system is in thermal equilibrium or not? And if you're going to tell me, oh, it's every observable in the system, well, this will fail. This will not work for every observable. Because we can, by construction, if I'm allowed to write down an observable by just telling you what its matrix is in the energy eigenstate basis, certainly I can invent observables for which this smoothness property is not true. So to the extent that this smoothness property is key, and I claim it is key, it can't be true of anything you're allowed to write down. It must be true at best of some physically relevant class of observable.
I see. Okay, thank you.
There's another question by Dario Rosa. Dario, please.
Yeah, I mean, probably Mark essentially already answered it. Or let's say, I wanted to say that what Kisok was saying, let's say, the fact that you bipartite your system in two and so on, is probably sitting in the assumption that that A varies smoothly with E. I mean, local observables have typically this property that they don't matter. Let's say the specific eigenstate doesn't matter much. If you start to take crazy observables, they will depend crazily on the various eigenstates.
Right. So the crazier an observable you take, the more likely this is to fail. So
Yes.
There's some work by Tarun. Now I'm blanking out on his last name. That says that you can take up to half the system size and get this to work. But if your observable has more than half the degrees of freedom in it, then it will start to fail. Tarun Grover, excuse me. So yes, so we have to restrict our class of observables. They definitely should be something that has physical significance in something like a spin system, and they should involve no more than a few of the fundamental degrees of freedom. If you're starting to build observables out of half the degrees of freedom, or some number that's scaling with n, then this is likely to fail. So I always had in mind that the number of observables is small. That the observable is built out of a small number of degrees of freedom. But there's some indication that that small could mean up to half. All right. So this is the conclusion, and this is part of eigenstate thermalization, which is a phrase I used in this paper in 1994. There's an earlier paper by Josh Deutsch, which comes to a very similar conclusion on the basis of random matrix theory, thinking of a perturbation of a system by a random matrix. And there are many antecedents in the literature for specific systems, which I'm not going to try to go through the history of, but many people have had closely related ideas, usually in the context of some specific problem they were interested in. There's this very nice review from a few years back by these folks. I believe it was Marcus Riegel and his collaborators that added hypothesis to eigenstate thermalization at some later point. All right, that's all right. So this is the claim at this point is we can understand this equality or near approximate equality because it is subject to these the uncertainty of discrepancies due to the quantum uncertainty in the total energy. We can understand this part if the diagonal matrix elements vary smoothly, but I have not at all shown you that that is true in any system. Okay. Now we have the rest of the terms, and these are the quote fluctuations, unquote, which really just means any deviation from the thermal value. And these are supposed to be small in the sense of either being small most of the time or being rare. And so we still have this issue to understand. But this one is in principle easy. The answer is this will be small most of the time if the matrix elements themselves are small. Again, small has not yet been defined, but if all these matrix elements are small, then this sum will usually be small. However, if we're very clever and we very cleverly choose C coefficients, then even though all these matrix elements are small, at some particular time, like time 0, we may be able to get them to line up and add up coherently and be something big. And we know that that has to be possible because we know we can create states which are not equilibrium states, in which these expectation values will be far from the equilibrium value. But then the idea is that now as time goes on, that's going to introduce phases here. And once these phases turn on, the coherent summing of over alpha beta, in which the C's were picked to get these to line up and add coherently, that coherent addition will be messed up by the phases, and then this will reduce to being small again, because each of the individual contributions is small, and they're no longer adding coherent. Okay, so now the question are these conditions do they ever happen? Do we know of any systems in which the diagonal matrix elements very smoothly, diagonal elements in the energy eigenstate basis, very smoothly with the index or equivalently with energy, and where the off-diagonal matrix elements are suitably small? And happily, the answer is yes. This is known to be true for quantized chaotic systems. And this is what I learned by going off and reading the quantum chaos literature back when I was first thinking about this. And all right, so how does that work? Well, quantum chaos is a really interesting subject. First of all, classical chaos is an interesting subject. A very simple system one can look at is a so-called billiard system, where a particle is just bouncing around inside, classically is bouncing around inside some boundary. And of course, then this could be in any number of dimensions, but 2 dimensions is the simplest to think about and draw. And the motion of the particle can either be integrable or chaotic, depending on the shape of the boundary. The question is whether the boundary shape allows for there being an extra conserved quantity or not. So in a square or a rectangle, the extra conserved quantity, in addition to the energy, you could say the individual magnitudes of the individual momenta in the x and y directions are conserved. Of course, the energy is the sum of the squares of those, so that's one. But then there's another one. In a circle, it's angular momentum. In an ellipse, it's some distorted angular momentum. But we can figure out what it is. But then there are chaotic billiards, the so-called Sinai billiard, which is a circle inside a square, the stadium billiard, which is 2 semicircles connected by a straight line segment, the cardioid billiard. And in these shapes, motion is chaotic. Now, I'm not going to spend time defining what chaotic motion is. Classically, one thing that it means is that any uncertainty in the initial conditions grows exponentially. If you know where the particle is at time 0 to within some range, that uncertainty grows exponentially fast. There are other things we could use to define it. But here, just looking at these pictures, which are by Arne Baker, who's done a lot of great numerical work, these are nicely, just looking at them, you can see the difference. But now we could ask about quantum mechanics. So we want to do quantum mechanics. So I want to think about what is an energy eigenfunction in one of these shapes. Well, inside it's just a free particle. So a plane wave is a solution of the free particle Schrodinger equation. But then we need to add up plane waves such that the complete wave function vanishes on the boundary. That's the quantum mechanical boundary condition that corresponds to hard walls that we all learned in the particle in a box problem in our first course in quantum mechanics. So to do that, we're going to superpose different plane waves, that is, plane with the different wave vectors. The wave vectors should all have the same magnitude because the magnitude is just related to the energy, but they can have different directions, as shown here on this little diagram. And then we can superpose them with different coefficients. Here I've called the coefficient C. These are different C's than the previous C alphas. I should have given it a different name, but and J is a different index than we've had before. This is just counting different possible directions. We want to sum them up, and we want to try to get the wave function to vanish on the edge. That will only be possible for certain magnitudes of K, which correspond to the energy eigenvalues. Okay, this is impossible to do except in this, the solvable integrable systems. This can't be done analytically in the chaotic systems, but computers are very good, and so we can use computers. But in 1977, Michael Berry, who's done a lot of wonderful work in many areas of physics and especially quantum chaos, had a conjecture that if you figured out what this eigenfunction was, and he was making this conjecture at a time when there were not computers that could figure them out, that they would look like Gaussian random numbers. And in particular, they would be uncorrelated from one K to the next, even for nearest neighbor Ks. So knowing one C would tell you nothing about the next C, and they would have a Gaussian distribution. It's actually the uncorrelated part that's most important. And this was a beautiful conjecture, which turns out to be true. So here's more pictures from Arndt. Here is on the left is random waves in which Arndt chose those C coefficients with a random number generator. And here's an actual eigenfunction in the cardioid billiard. And you're supposed to look at these two pictures and think, yeah, those look very similar. Okay. So one can, of course, do more sophisticated tests. Here's a simple one. A Gaussian distribution of the C's predicts that the wave function itself has a Gaussian distribution of its amplitude as you look if you pixelize it. And so Arndt again did that. And so the blue histogram is the pixelated amplitude distribution. Underneath it, which you can barely see, is a red Gaussian that has no free parameters. The width is just controlled by the normalization of the wave function. And you can see it's a perfect fit. So this conjecture of Michael Berry is a very prescient conjecture. We now know from numerical evidence in these systems, it seems to work extremely well. Now, what is a random?
In the previous page, in the left-hand panel, classically, classically, it was integrable. It was integrable classically, but in quantum wave function, you show that it was chaotic. So,
well, we have to distinguish whether we are working with an integrable system or a chaotic system. The wave functions will not obey Berry's conjecture in integrable system.
So can I have some clue to guess what some variable in classically integrable system can be quantum mechanically chaotic? So in this boundary condition.
I'm not quite sure what you're asking.
I'm asking is in left box was integrable in classical mechanics, but in quantum mechanically you show that it follows the various random wave conjecture, coefficient C. Yeah. So can I have some clue, some insight, and how such classical integral system can be quantum mechanically chaotic? Is there any clue to guess it, or?
I don't know any more than I'm telling you. Michael Berry had this intuition that this should be true for chaotic systems. It's not, of course, true for integrable systems. There we can solve them, and the wave functions have regularities that we all know because we all learned quantum mechanics solving integrable systems like the harmonic oscillator and the hydrogen atom and things like that. And there we get these very definite regularities that we can compute and see. Barry's intuition is that chaotic systems would be different in that you would not get, so in a rectangular billiard, for example, we would only be summing two plane waves, one that goes along one rectangular direction and one that goes along another. Barry's great intuition was that we should sum them all now, basically, with random looking coefficients. But the thing I want to point out here is that what do these random looking coefficients do for us? If we look at this wave function, we see these ridge lines and so on, but if we squint a little bit and imagine washing these out on some scale, it now looks more or less uniform. On a large scale, we've uniformly covered the position space, and according to this arrow diagram, we've also uniformly covered momentum space. These point in all the directions, and we've added them up with different coefficients, but on the average, they're all have the same, they're all selected from the same distribution. So this is something that's uniform in both position space and momentum space. And this happens more generally. If you have a random wave function suitably defined, and I'm not going to try to go into the details of how one would define this. And then you ask, what does that look like classically? And there are techniques to do this. The Wigner distribution, if you've heard of that before, is one. They look like a uniform probability distribution. If you suitably smooth out things on the scale of the quantum wavelength, they look like a uniform probability distribution over a constant energy surface in phase space, which is exactly the classical microcanonical ensemble. So a random wave function, as Barry predicted and as we see numerically works, if you look at it on a smooth, by smoothing it out, looking at suitable observables on that, in that wave function that you could measure with inside that wave function, you will get a classical microcanonical result. And this is actually corresponds, there's actually a mathematical theorem about this due to Alexander Schnirelmann, which says that if you look at a diagonal matrix element and you think about it in terms of powers of h bar, which quantum chaos people like to do, the 0th order term is indeed the classical microcanonical average of A in a chaotic system. And then there are h bar corrections. For someone like me who wants to set h bar to 1, what this means is you have to go to a high enough energy. You have to go to a high enough energy where the quantum wavelengths are, I can look at an observable that smears over many quantum wavelengths. And the nice thing about this is there's an actual mathematical theorem, which is, as we all know in physics, rigorous math is hard to come by. But here we have an actual example. And we don't really, I've been now emphasizing the classical connection, but we don't really need it. Because the thing we needed was that the A alpha alphas, which I'm now writing in this other notation, vary smoothly with energy. But certainly the classical microcanonical average of some classical observable varies smoothly with energy. And not only does it vary smoothly with energy, but so does this correction. And so does the next correction and the next correction and the next correction. And you actually have to get to an exponentially large number of corrections before you start to get to something that's wiggling fast enough to not be smooth in the sense we need. So Schnirelmann's theorem is both too strong and too weak. It's too weak in the sense that we also need these corrections, but I'm probably saying this backwards. We don't act, what we need is smoothness. And here's a set of examples where we can get it. If we know we can get it rigorously, that if we quantize a classically chaotic system, we will get the smoothness we need. Now, the off-diagonal part is not quite as rigorous. We want to show that these things are small. The random wave conjecture tells us that these off-diagonal matrix elements should vary erratically with alpha and beta, because you change the energy, you now get a completely different eigenfunction. And this will now be some just different thing, and you will get a different number. If we choose to look at the variance, so I'm going to subtract off its expectation value in this energy eigenstate, square it, and then take the expectation value of that, I can turn that into a sum of the squares of the off-diagonal matrix elements. Now, this left-hand side, if A is something like a spin or the momentum of a single particle, pretty much any physical thing you can think of, the square is going to be a number of order 1 also, right? So if I'm working in units where A itself is order 1, its square is going to be order 1, and then this will be an order 1 number. On the other hand, here, I'm doing a sum over energy eigenstates, and even if we say these matrix elements falls off rapidly in energy difference, there's still an exponentially large number of these. It scales like e to the average energy between these two. And so there's a really large number of these, and so we can think of this as this large number, the number there are. S is the thermodynamic entropy, which scales like the number of particles, times some average value. So this is huge. So this must therefore be small. There are a couple of ways it could be small. One is just most of these are small, or they're all small. The other is most of them are 0. Most of them being 0 is what happens in certain integrable systems with their selection rules. And then just different energy eigenstates are labeled by different conserved quantum numbers. And if A is an observable that only changes a few of those quantum numbers, then most of these matrix elements are going to be 0. And that's how this sum can end up being small. In a chaotic system, there aren't supposed to be any conserved quantities. And so there's no reason for many of these to vanish. And so in that case, they all must be very small. And so we conclude in a chaotic system where we have no reason to think that a lot of these are 0, that they are all really, really small. Sorry, I've hit the wrong key again. Okay, so this is the other piece we needed. How small are these off-diagonal matrix elements? The answer is they're really small. And these are controlling these fluctuations. So these fluctuations of the expectation value around the thermal value are all very small and well below any sort of experimental tolerance we might want to set. Okay, I'm getting to towards my hour here, so let me say a couple more things. This is now there's now there's a formula that is often synonymous with ETH, and I approve of that way of thinking about it. This is a formula I wrote down a few years later. What do this matrix elements look like? There is supposed to be a smooth diagonal part. So here E is the average of the two energies. Of course, here we have a Kronecker delta, so there's really only one energy. Omega is the difference.
Question, may I ask one more? Sorry. In the previous page, I still get quite understand how the random wave conjecture give this argument in the intermediate system. Can you more elaborate that part?
Well, the argument is just there are two ways, roughly speaking, there are two ways the sum can come out small. One way is if most of these are 0. And in integrable systems, that can and does happen, and we understand it. In a chaotic system, we don't have an argument that's going to tell us that most of these are 0, or even any of them are 0. There's just not a reason for it to happen, and one can check numerically for different observables that, in fact, it does not happen. Basically, another way you can think about it is alpha and beta are orthogonal. And so, A being, if we think of it, A as a local observable, it can't change very much about one of these states. So they're still almost orthogonal, and that's this smallness. again, integrable systems and with a specific class of observables are special in that there we can and do find that most of these are zero. But if they're not mostly zero, then they all have to be small. That's the argument.
So yeah, my question is inserting the wave function explicitly, and I perform some average integration, and I can use the Gaussian distribution for C alpha. Then I will derive this. That part I got quite my image. I did not. Yeah. So yeah, how starting from that just a random wave. I mean conjecture mathematically. Yeah.
Oh yeah, starting from the random wave conjecture. Yes, then you can do this. If you're willing to start with the random wave conjecture explicitly in some particular case, then you can just do this explicitly, and you will find this is true.
I see, but yeah, let me think more.
I mean, it would take some slides I don't have to go through the details of
Yeah, we have a question from Dominic Safranik. Dominic, please.
Yeah. So I wonder still, because you said that this variance on the left-hand side is of order 1. I didn't get that argument. Could you repeat it? Maybe more elaborate on it?
Well, I mean, of course, we need to know something about what observable we're talking about. But, if it's a spin, for example, if it's a component of a spin, then it has eigenvalues plus or minus 1, and then this is bounded by 1. If it's a single particle kinetic energy, say, then again, it's these things are bounded, and it's just not the case that they're going to be large, and certainly not exponentially large, which is what they would need to be for this not to be exponentially small.
So it could be smaller than exponentially small.
It could be, yeah.
Okay, because if you
As
say
far as
they're
I
just
know,
bounded, then it's upper bound is exponentially small.
Yeah.
Okay. Thank you.
Okay, so basically, keep hitting my keypad here. We can summarize all this in the following formula. Again, there's a smooth diagonal term. Then there's an off diagonal term, and there's this smallness factor, e to the minus the thermodynamic entropy over 2. There's an envelope function that depends on both the total energy and the energy difference. And then there's some, quote, random, unquote, number. Of course, they're not really random because we could compute them in principle, but you should think of them as varying erratically and having an average. If you did some average of them over ranges of alpha and beta, they should average to 0, and their squares should average to 1. And so that's by definition. And so the secular variance of the size of these with the energies is controlled by this F function. And it's also E, as I've said a couple of times, we should think of as scaling as the number of particles, but the energy difference we should think of as scaling as order 1. It turns out that Fourier transforms of this F function control time dependence. And so if we have a system like a box of gas where the relevant time scale should be something like a mean free collision time, that's a number that's order 1. And so most typical systems will have the relevant time scale for dynamics is an order 1 time scale. And that turns out to mean you should think of omega here as being order 1. Or another way to say it is, if we look at the variation of this F function, it will vary with omega. If you change omega by an order 1 amount, F will vary a lot. On the other hand, E you should have to change by an order n amount to get F to vary a lot.
Mark, we have another question by Dominic.
Yes.
Yeah, I wonder about that F function. So you say it's an envelope function. What does it mean how it scales with E? Is it like bounded or?
No, well, it can be related to a certain 2-point correlation, time correlation function of the observable. properties like whether it's bounded or not depend on the system and the observable. And
Yeah, I just
there's sort
wonder
of-
whether it could be something like of order e to the s of e,
No,
which would
no,
fill the.
no, it is not. I mean, that's, well, again, in these systems, in chaotic systems where these off-diagonal matrix elements are not mostly zero, that's why this e to the minus s over 2 is out in front. So we should think of f itself as a function of order 1.
Ah, okay. Okay, thanks.
Yeah. Okay. So I wrote papers on this in the 90s, and I started going to quantum chaos conferences. And I learned a lot of really interesting stuff about quantum chaos, but there wasn't a huge amount of interest in statistical mechanics and foundations of statistical mechanics. However, this all changed about 10 years later due to experiments. David Weiss at Penn State and his group did a very nice atomic physics experiment, and these are this is all stuff taken from their paper. They did a very nice atomic physics experiment in which they took 2 clouds of cold atoms. That's these purple things here. Well, I guess they started out as 1 cloud and they separated it into 2 clouds in essentially 1 dimension. So this is all being done with laser traps, and they had strong traps in the other 2 directions so that the clouds did not disperse in that direction, and a weak harmonic trap in the 3rd direction in which they could get these clouds to separate and then come back together and then merge and then separate again. And this is their actual experimental data showing the separated clouds coming together, separating again, coming together, separating. And they called this a quantum Newton's cradle. Newton's cradle is this toy that you may have, I don't know if I should call it a toy. I bought one of these when I was like 12 years old because I saw this in a store. And it was fascinating to me. You take the one set, it's 5 balls typically, and you can pull like 2 of them up to the left and 2 of them up to the right, or 1 of them, and let them collide and they bounce off like this, which is kind of interesting. You can also do other interesting things with them. So you can ask, why did this happen? The naive thing that would happen is once you form a single cloud, it will thermalize and sit there. The experimenters understood that this does not happen, and they understood why, and the reason is very simple. In 1 dimension, if you collide 2 particles, conservation of energy and momentum means all they can do is exchange their 2 momenta. They either go through each other with the same momentum or they bounce off and exchange momenta. And so there's no mechanism. Well, 3-body collisions, instantaneous 3-body collisions can actually do something different. But if you ignore those, then nothing can happen. They can't change their distribution of magnitudes of momenta. And that's exactly what they saw in their experiment. But then they said, okay, we understand this, but still it calls into question naive statistical mechanics. When does it work? When does it not work? Okay. And now that there was an actual experiment, suddenly a lot more people were interested. And in particular, this group, Marcus Riegel, Vanja Junko, and Maxime Olshani, then all at the USC, did some numerics on a hardcore boson system. They either did some lattice, irregular looking lattice, where they put all the particles on 1 piece of the lattice and then at time 0 opened a door and let it spread throughout the lattice. And in this case, and then by sheer coincidence, as they were working on this, I happened to pay a visit to USC, and we met and we talked about all this stuff, and they told me about this experiment and how they were working on understanding it. And I said, oh, well, I wrote these papers and back 10 years ago, maybe you should check if that has any relevance, and it does, right? So they were able, here they're following a particular trajectory, and they see it thermalizes to this value, and they are comparing it to either a canonical or microcanonical expectation value. They only had, I think, 5 particles. So canonical and microcanonical differ. Microcanonical is better, and it works, which it should be when you only have 5 particles. And this is a plot of really a bunch of different observables. They're looking at Fourier components of a number density. And what these lines all lying on top of each other are showing is that the diagonal matrix element of 2 different energy eigenstates agrees with the microcanonical average. So this is the diagonal ETH, that individual energy eigenstate expectation values are all the same in a suitably small range of energy. They were able to check. Yes, question? No? Okay, so they're able to check that.
Mark, let me ask one question. You just mentioned that in this
Yes.
previous experiment, that in the bottom figure, that they used a Fourier transform. So basically an extended observable, which is a sum over many
Yes.
Local ones.
Yes.
And but before you said that these are not good if they involve more than 1/2 of the numbers of degrees of freedom. So how comes?
Well, it's really, I mean, they chose to do it this way. I would not do it this way. I mean, what you can unfold these. So this is a Fourier component of a spatial number density. If I knew all those, I could reconstruct the individual spatial number densities. So I wish they had plotted this versus the spatial index instead of versus the wave number index. But those are just linearly related by the Fourier transform. So what they're really, I would say what they're really doing is they are looking at a local number density, but they're looking at it at every point.
Okay.
And then they chose to express that as a Fourier transform, which I wouldn't have done, but
Perfect. Yeah. Thank you.
that's what they did. Yeah. Okay. And then for an integrable system, which now they have just a single lattice line, and that system, hardcore bosons on a linear lattice, turns out to be integrable. It's not completely obvious, but it is. And now basically it doesn't work anymore. The same plot where everything was on a single line, now different eigenstates give different answers. The microcanonical distribution is different than which is now just a sum over many energy eigenstates, is different than any individual eigenstate, and so on. So this shows the difference between an integrable system not obeying the ETH matrix element ansotz, whereas a chaotic unquote system does. Now, hardcore bosons are, of course, a quantum mechanical thing. We don't have a classical limit for them. So the ETH ansotz is now, on the basis of numerical evidence, believed to hold whenever the system is sufficiently complicated that you could think of it as chaotic, even if it doesn't have a nice classical limit. Okay. So, all right, and here it says this, there are systems that don't obey ETH, integrable systems. In this case, you need a temperature-like parameter for every conserved quantity. And in a true integrable system, there are an infinite number of those, or at least a number equal to the number of degrees of freedom. And then you should do something called a generalized Gibbs ensemble with this same set of authors, with Yurovsky explain how that should work, actually before the previous paper. Another thing that can happen, which I think you had a colloquium by David Hughes, is that right? Many body localization, if you have disordered systems, they can fail ETH because they localize. The energy eigenfunctions don't spread over the whole system. They get stuck in certain patches. And this does not have a classical analog. It's a purely quantum phenomenon, but it's one that also, there's a sort of quasi-integrability in that case, or an effective integrability, and those systems don't obey eigenstate thermalization. And so, if you want a system like that to thermalize, you either have to further restrict your class of initial states, or what very often happens in the real world is it's actually coupled to something else, because it's very hard, of course, in the real world to isolate anything. Okay, I have a couple of transparencies on entropy, but since we're already 15 minutes over, I'm going to skip them and go to the conclusions. I will go back to them if anybody wants to hear me, but it's kind of off topic. It's off the main topic. So let me go to my conclusions, which is that this eigenstate thermalization hypothesis, which is a hypothesis about what matrix elements in quantum mechanics look like. It's purely quantum mechanical, doesn't have anything to do per se with statistical mechanics. And it's motivated by known and in some cases rigorous results from quantum chaos theory. If that ansotz holds, then we can understand how you can put a system in a pure quantum state. You get to choose the initial state. All we ask is that its energy uncertainty be small enough that it's not going to destroy a meaningful definition of temperature for such a system. If that's true, and this matrix element ansotz holds for the observables you're going to look at, then you can understand how those observables come to approach thermal equilibrium values and then stay there most of the time. And all right, I already said this part, quantized chaotic systems are known to obey this. But one of many topics still under discussion and active research is, well, exactly what are the boundaries? Somebody just hand you a system, what category is it in? How do we know? This is still not well understood. And is one direction one can try to pursue to go farther. So that's all I have to say. So thank you for your attention, and I hope this was useful to you.
Yeah, thank you very much, Mark, for this fantastic colloquium. And so let us all thank to Mark and clap our hands. Thank you. Bravo.
And I'm happy to answer any more questions.
Yeah, we still have ample time for questions. So who wants to start? If no one, let me ask you a first question about these fluctuations of an observable A of t around its thermal average, starting from some maybe unusual initial state, and then it comes to these small fluctuations. What happens if you you tune your system, your Hamiltonian, closer and closer to an integrable one? Would you expect, is there anything known about how the properties of these fluctuations, amplitude and characteristic times will change?
Yeah, well, yeah. So this is a subject of which there's been a lot of work. If as you come closer and closer to an integrable point, of course, this picture breaks down, right? And so you will see larger and larger fluctuations, and you will see more and more dependence on the initial state. And how this transition occurs, how well, and coming at it from another side. Suppose we have an integrable system and we add a small non-integrable perturbation to it. How big does that have to be? Some results that suggest that it can be algebraically small in n. That is something that's like 1 over the square root of n can be a large enough perturbation to destroy integrability in a many-body system. But this is another subject. Or one could ask, how low in energy can you go? I said energy should be scale like the number of degrees of freedom, but what if it scales like n to the 3/4? Is that good enough? Okay, so there's all sorts of questions one can ask about the boundaries of these ideas and what happens at those boundaries. And I think, that's something that's still being explored, and we don't have clean answers for most of it.
Yeah, we have a question from Dominic, please.
Hi. Yeah, I would be actually partly interested in those slides about entropy because during my postdoc with Josh Deutsch, he studied actually just this thing, but in different notion of entropy. So
Okay, well, thank you for asking. Now I can give my slides on entropy. I'm going to define entropy the way von Neumann would define it as minus trace rho log rho. But I put a tilde rho meaning the density matrix of the system or density operator, which will take to be time dependent. So there's a time dependent entropy minus trace rho tilde log rho tilde. But the question is, and so I will consider entropies that are all defined like this, but the big question is, what should we use for rho tilde? So here are some options. One is use the exact quantum state. This is what von Neumann would have called the von Neumann entropy. We take the quantum state, which I'm always taking to be a pure state, and so the density matrix is just ket bra of the state. And then the von Neumann entropy is 0. It's 0 for any pure state. So this is a very uninteresting entropy. It's always 0. Doesn't tell you much. Something that's received a lot of discussion and which I also had played some role in is the notion of entanglement entropy of a subregion. And here I'm thinking of it in particular of a small subregion. So I take the actual pure quantum density matrix, but now I imagine degrees of freedom that either live in subsystem 2 or subsystem 1, and I trace over the states of all the ones that are in subsystem 2. This now gives me a density matrix that lives only in subsystem 1, and generally, unless the original psi was a product state of a state that lived in system 1 and a state that lived in system 2. In general, this entropy will not, or this density matrix will be a mixed state density matrix, and it will have a non-zero von Neumann entropy. Another notion of entropy, which I call the Jaynes entropy due to Edwin Jaynes, who, if he didn't invent it, at least talked about it a lot, although in a classical context mostly. But the quantum version is, again, I'm going to imagine I have my list of observables and that I know what their instantaneous time expectation values are. And I also know what the total energy is. And every density matrix should be normalized to have trace 1. That's just that probability should sum up to 1. So the Jaynes entropy is to ask for a rho tilde which reproduces these known values. So we insist that our rho tilde trace rho tilde AI give the known actual quantum expectation value and so on. But then we ask for the rho tilde that, subject to those constraints, maximizes the entropy. And then you get this generalized Gibbs ensemble form, although this is not really the generalized Gibbs ensemble. I misspoke, because these A's are not conserved. These are observables, but it's a straightforward exercise to do this computation with Lagrange multipliers. And you get the following result. You get e to the minus beta h, but now your beta is time dependent. And you get e to the minus gamma for each a, and all these things are time dependent. And we adjust their time dependences to match the known time dependence of the a. Now, the point I want to make here is that, well, one point I want to make is that this is actually equivalent to entanglement entropy. Oh, okay. If I say that my A sub i's are all the observables that live in region 1, and I'm hoping not to get into trouble by making region 1 sufficiently small, if I say that the AIs are all the variables that live in region 1, and I know all their instantaneous expectation values, that's enough information to reconstruct this density matrix, which then has to agree with this, because that's all it could be. So 1 and 2 are the same if A sub I is a complete set of observables in region 1. Now, the nice thing about we can also do the thermal computation where we write down a thermal density matrix and compute a thermal entropy, which is just given, and this is the absolute standard textbook calculation. And the nice thing about the Jaynes entropy is that it's bounded above by the thermal entropy, because the thermal entropy is the same as the Jaynes entropy, except we don't put in these constraints of the A sub i's. And if you put in more constraints, you're guaranteed to lower the maximum value, or at least not increase it, right? So this entropy has to be lower than the thermal entropy. If the A sub i's all have their thermal expectation values, which I argued should happen in a system that obeys ETH after enough time, then these are not actually new constraints, and the Jaynes entropy will be equal to the thermal entropy. So the Jaynes entropy starts for a non-equilibrium state at a value below the thermal entropy and then generally rises to be the thermal entropy. So this is my favorite notion of entropy. It ties in with the ETH idea that you should tell me what your observables are before we discuss anything. And then we can define an entropy in terms of those observables. And it has all the properties that you would like an entropy to have. It generally increases as the system approaches thermal equilibrium. This entropy increases, and when the system gets to thermal equilibrium according to the measured values of your observables, then it's equal to the conventional thermodynamic entropy. So that's my 2 slides on entropy.
Okay, thanks, Mark. And more questions, please. I see also there is a seminar room, I guess, at the ABCDP with people in there, which is unmuted. So just go ahead and ask questions from there, if there are any.
There are any?
I see some people there, but they are very small.
Okay. Well, let me thank
Mark,
you.
can I ask you another question? Coming back again
Yeah,
to that observables which involve more than 1/2 of the degrees of freedom might cause problems in this entire concept. Again, this is why I also hooked up on this Fourier transform of the density, because there are observables like for instance, say if I was able to measure, I don't know, phonons or some the occupation numbers of some quasi-particles of fermions in some Fourier space. Technically, they seem to be linear combinations of all degrees of freedom. Yet right. I would think they also thermalize pretty well, right?
No, right. They thermalize pretty well. And so when I've been speaking loosely about observables that depend on many degrees of freedom, we have to decide whether we're adding them or multiplying them. Right? So if you're adding them, then I can just as well think of them individually and say, well, you want to add them at the end, but I'm just going to look at them one at a time. And then I don't care how you add them. But if we're multiplying them, that's much different, right? If I multiply them, I can't tell them apart. So when I say an observable that depends on many degrees of freedom, I really mean I want to multiply them together.
Okay. Thank you. That's interesting. Okay, more questions?
Can you hear me if I ask like this?
Yes, please.
Okay, so when you write rho thermal for the second case, where A is a complete set of region 1 observables, I would naively want to take rho thermal to be the thermal density matrix inside the subregion.
So this slide is not well organized. There should be some sort of line here. So this same as 2, that should be thought of as this part. But now I'm introducing a new notion of the thermal entropy of the whole system. Now, what should happen to this guy, if it's a complete set of region 1 observables, is after the system equilibrates, this should be equal to e to the minus beta h1, right? Just the region 1. And this will be true, or at least approximately true, provided that we can think of, what did I do here? Oh, here's my picture. There's a surface to volume effect, right? So subsystem 1 has to be coupled to subsystem 2 somehow. So there has to be a piece of the Hamiltonian that lives on the boundary. And this final density matrix at late times should be equal to e to the minus beta h1 to the extent we can ignore this interaction. So, and we should be able to ignore it if we can think of it as a surface effect, provided the volume of H1 is big enough. So if H1 is just a couple of lattice sites, then the surface effect is going to be large, and then you won't just get e to the minus beta H1 in that case. You will get e to the minus beta H1 if the interaction between systems 1 and 2 is sufficiently small compared to system 1 all by itself.
So do I have to take the strict thermodynamic limit where the surface term roughly just disappears in order for this statement to be accurate? Or if I consider some small coupling, is there a sense in which this thermal density matrix picture holds away from n equals infinity?
Yeah, it holds to within an approximation, right? So it will be e to the minus beta h1, and then plus something that's suppressed by an area over volume. Okay, is that area over the volume sufficiently small that you can neglect it? If so, then neglect it. But if you want, rigorous absolute statements, then no, right? Then you have to take some limit. I like to think about, I like to think about things that are I want to make a statement that's correct up to some correction whose size I can estimate. Now, if somebody then wants to take a limit in which that correction goes to 0, okay, but I don't find these limits especially interesting, right? I mean, I want to know in a system where I'm actually saying how many degrees of freedom I have, to what extent is something that I want to say true or not true. And nothing I say will be absolutely true. There will always be 1 over n type corrections to everything. The question is n large enough that we can neglect those to whatever approximation we're trying to work? Does that answer your question?
Yes.
Okay, there's a question by Alexei. Alexei, please.
Yes, I'm wondering whether the ETH encodes in some form the timescales involved in the relaxation. So if by looking at the, say, studying the statistics of the off-diagonal, well, say of the function f or the matrix R, you can say something about how long would it take to actually reach this equilibrium, because I guess there are systems where things go fast, but there are also systems where you have a huge prethermal regime.
Right. So that's all encoded in the omega dependence. Well, the simplest version of it is encoded in the omega dependence of f. We could write down a 2-point time correlation function of a, right? So I probably don't have a slide with this handy. So you consider Heisenberg picture operator A of t, and now it turns out the nice thing to do from this point of view is to take A of t times the square root of a thermal density matrix times A of 0 times another square root of a thermal density matrix and take the trace of that. That, it will turn out, is the Fourier transform of the absolute square of f. So to the extent that that the thermalization time is encoded in this 2-point correlation function, which is somewhat funkily defined with this split thermal density matrix, that's completely controlled by the f function. So time scale is built into the f function. And the f function is system and observable dependent. So there's no general theory as far as I know of the f function, and there sort of can't be because we know systems behave in all sorts of ways. Even systems we would want to say are fully chaotic, they can have all sorts of complex behaviors. And those are the simplest of those are encoded in the F function. More complicated things that like the out of time order 4-point correlation function that people talked about a lot a few years ago, that turns out to be encoded in subtle correlations of these R's. You can't treat them as independent Gaussian random variables, which I used to think you might be able to do. That doesn't work. And if you do that, you will definitely get wrong 4-point functions. So there's a lot of subtlety in here, but the most basic time dependence is built into the into the omega dependence of the F function.
Okay, thanks.
Yeah.
Okay, last call for questions. Should not only forget, not only think that we are tired, but I think also our speaker is probably very much tired, and I don't know what the
my
time.
dinner time here in California. So.
Okay, so he's hungry as well, and I hope dinner is ready. Anyway, last call, last question. Oh, Alexei, make it quickly.
Yes, I mean, a very quick question. Has ETH been tested for glasses?
Glasses.
Yes.
I don't know. I suspect not. I mean, there's not a lot of quantum glasses work as far as I know, but
Okay.
I am not in that community at all. I have no idea.
Okay, thanks.
Good. Then with that, I think we can finish the question part of this colloquium, and let's thank Professor Mark Srednicki once again for this fantastic presentation. Thank you, Mark.
Thank you. Thank you for the invitation, and I hope to see some of you in person in the not too distant future.
Thank you very much, Professor Mark, and also Professor Srednicki. Yeah, thank you very much.
Thank you.